So having had a go at working out oxidation and reduction reactions, we're now going to move on to look at oxidizing agents and reducing agents. Now this takes a little bit of getting your head around. So an oxidizing agent is something that brings about oxidation. To do that, it itself is reduced. So an oxidizing agent is very easily reduced. In other words, it's very good at gaining electrons. A reducing agent, on the other hand, is something that brings about reduction. It itself is oxidized. So in other words, a reducing agent is something that is very good at losing electrons. Let's look at a couple of examples. So we have the reaction copper oxide with magnesium, forming magnesium oxide and copper. So the oxidizing agent is the species that causes the oxidation. Well, in this reaction, it's the magnesium which is being oxidized. So the oxidizing agent, the agent that's causing the oxidation, is the copper oxide, the CuO, because it's forcing the magnesium to lose 2 electrons. Copper itself is being reduced from the Cu2+ to the Cu stage. The reducing agent, on the other hand, is the magnesium, because the magnesium itself is being oxidized and it's causing the copper to be reduced from the Cu2+ stage to the Cu. The next example is zinc and chlorine reacting to form zinc chloride. In this case, the oxidizing agent is the chlorine, because it's causing the zinc to be oxidized from the zinc 0 oxidation state to zinc 2+, and it is the zinc which is the powerful reducing agent, because the zinc is able to reduce the chlorine from 0 to -1. It itself is oxidized. Last example, copper sulfate with iron reacting to form iron sulfate and copper. Well, the copper sulfate this time is acting as my oxidizing agent. The copper is being reduced from the 2+ state in the CuSO4 to the 0 in the elemental copper. So that is a reduction reaction that's causing the oxidation of the iron. The iron is being oxidized from Fe0 to Fe2+. It is causing the reduction of the copper from Cu2+ to Cu, so it is my reducing agent. We will come back to oxidizing and reducing agents again, because as I said, it takes a little while to get your head around those. But so far we've only looked at ionic compounds, and if we could only apply redox to ionic compounds, it wouldn't be a very useful tool. However, we can apply them to covalent compounds. Now obviously covalent compounds don't have charges. We get around this by assigning them an oxidation number. So the oxidation number is the charge the species would have if the bonding was 100% ionic. So we're going to pretend in this covalent bonded reaction that all of these are actually ions. So in this case, we're going to say that the oxygen here has gone from O0, so it has no charge on it, and we're going to assign it a charge in the water, and we're going to say it has the charge of -2. The hydrogen, on the other hand, is starting off as an element, and it's going to this covalently bonded compound, but we're going to assign it a charge of +1. So in this case, the hydrogen has been oxidized and the oxygen has been reduced. And we can even do a half equation for that. So you've already used oxidation numbers. When we look at species like the copper 2 ion or the iron 2 ion, those Roman numerals represent the oxidation number. To distinguish an oxidation number from a charge, oxidation numbers, you write the sign followed by the number. A charge is a number, then the sign. So for example, SO4 has a charge of 2-. that is a charge because we put the number, then the sign. If you get it muddled up, if you put it around the wrong way, it really doesn't matter. You're not going to lose a mark for it. But that's how we can distinguish the difference between an oxidation number, for example, copper +2 and the sulfate 2-. That is an oxidation number. That is a charge. For ionic compounds, it's quite easy to assign the oxidation number because it's basically the same as the charge. So magnesium in MgCl2 would be +2. Sodium would be +1 because that's the charge always on those. Calcium, again, a group 2 element, has a charge of +2, therefore an oxidation number of +2. Potassium, +1. Slightly more complicated when we have species which can have variable oxidation states, such as iron and copper. Here we need to look at the other species. So oxygen, we know oxygen always forms a charge of -2. So therefore the iron, to make it a neutral compound, must be +2. And again, a chloride is -1. There are 2 of them. That makes the oxidation number of the copper +2. However, things are not always quite so straightforward when we're working out oxidation numbers, especially of covalently bonded molecules. So there are some rules that you need to understand. Most of them are reasonably straightforward. So for example, if you have an uncharged molecule or an uncharged compound, the sum of all the oxidation numbers has to add up to 0. That's why it's neutral. If in an iron, then the sum of all the oxidation numbers needs to add up to the charge on the iron. There are a few individual ones that you need to learn. Hydrogen is always +1. The exception to this is whether it's with a metal hydride. So for example, LiH, the H would be -1 because the lithium is going to be +1. Electronegativity, which you're going to be studying on the other side of the syllabus, is the ability of an atom to attract a bonding pair of electrons. Fluorine always has an oxidation number of -1 because it is the most electronegative element. Oxygen, which also is very electronegative, is -2 in all compounds except with fluorine or in peroxides. And in that case, in peroxides, it's -1, but with fluorine, it can be +2, because the fluorine, being more electronegative, can bring out the higher oxidation numbers. Chlorine, again, is -1 in compounds, with the exception of fluorine or oxygen compounds, because fluorine and oxygen are again more electronegative than chlorine and can bring out the higher oxidation numbers. But do remember, especially with covalently bonded compounds, that these are just the charge the species would have if the bonding was 100% ionic. In many respects, it's not real, it's just a way of us keeping track of where the electrons are. So I'm going to do a few examples for you, and then I'm going to get you to do the table at the bottom of page 4. So H2SO4. We're going to start with the species that we know the oxidation numbers of. Well, we know that the oxidation number of hydrogen is +1. Notice you always give the oxidation number for the individual species, never the parts of the compound. Oxygen is always -2. We don't have a rule for sulfur, so that's the one we need to work out. We do know that this is a neutral compound, so that the sum of the oxidation numbers needs to add up to 0. Well, I've got 4 oxygens. Each oxygen has an oxidation number of -2, so that makes -8. Each hydrogen has an oxidation number of +1, so that makes a total of +2. So therefore, to make the overall compound neutral, the sulfur must have an oxidation number of +6. The next example, KMNO4, well again, potassium, there's a rule for that, it's a group 1 compound, it must have an oxidation number of +1, and oxygen again must be -2. After all, it's not with fluorine and it's not a peroxide. Again, we can work out the oxidation number of the unknown, the manganese, because we know that this whole thing has to add up to 0. Got 4 oxygens, each of -2, that makes -8. Potassium is +1, so therefore the manganese must be +7. and that is its oxidation state. Next example, sodium is a group 1, so it's always going to be +1. Oxygen, well, it's not with fluorine and it's not a peroxide, so again it's -2. So we need to work out the chromium, which is our unknown. 7 oxygens of -2, that makes -14. 2 sodiums of +1, that makes +2. That gives you the chromium species in the middle. That must add up to +12, but there are 2 of them, so each chromium, and remember we give it for individual species, must be +6. Last example, potassium, again group 1 must be +1. Oxygen, on the other hand, is a -2. It's not with fluorine and it's not a peroxide, so again it's -2. Chlorine is usually -1, apart from in compounds with oxygen. So we have to work out its oxidation state in this case. You've got 4 oxygens, each of -2, so that would be -8. Potassium is +1, so that leaves the chlorine as +7. So chlorine is in its highest oxidation state of +7 because it's combined with oxygen. But again, do remember the ClO4- ion, this ion is a covalently bonded ion. So this is just a way of us keeping track of the electrons. It doesn't actually have a charge of +7. We're saying that it has an oxidation state of +7, and that's the charge the species would have if the bonding was ionic. So pause the video at this point and have a go at the table at the bottom of page 4. So here are the answers. A couple of the later ones that tend to trip students up is the oxygen in H2O2, because this is a peroxide. The oxygen has an oxidation number of -1. The hydrogen in lithium hydride, or LiH, well, that has an oxidation number of -1. Again, hydrogen is usually +1 except in a metal hydride. And last but not least, the sulfur in Na2S4O6 is +2.5. So remember, this is an oxidation number, and it's quite possible to have an oxidation number of +2.5. You can't have half an electron, but remember, this is the oxidation number, is the charge the species would have if the bonding is 100% ionic, and the bonding in this is not ionic, it's covalent. But this method works when we're just trying to count electrons, which is all we're really doing with a redox equation.